Hello, welcome to Basics of Finite Element Analysis. Today is the last day of the 6th week of these lectures, and what we will discuss today is how do we go around applying boundary conditions in context of finite element formulation of an Euler-Bernoulli beam. So, first we will look at different types of boundary conditions which are possible in context of beams. Okay. So, the first condition is free end. What is a free end? Suppose there is a beam end which is free, and then we will look at essential boundary conditions and natural boundary conditions. There are two essential boundary conditions which are related to W and slope, and then there are two natural boundary conditions which are related to shear force and moment, right. So, in case of a free end, we do not know W. Suppose I am having some load here, we do not know what is the value of load W, we do not know slope also, but what we do know is that at this end shear force is 0 and also the moment is 0. Okay. So, if this end corresponds to node 2, then in our equation, if that is the extreme end of the beam, then in our equation Q5 and Q6 will be prescribed as 0. Q5 is the shear force and Q6 is the moment. Okay. So, we have to look at each of the boundary and see what things we are going to prescribe. The second condition, possible condition, could be pinned end. So, pinned end could be something like this. In this case, the value of W is 0 and the slope is unknown, and because we at any point the shear force now we do not know, because this pin is exerting some shear force we do not know. So, this is unknown, but the beam is free to rotate at the pinned end. So, moment is 0. The third boundary condition is fixed end. So, what is a fixed end? It is something like this, and here I have rigidly fixed it. So, in this case W is 0 and so is slope, but shear force is unknown and moment is unknown. The fourth condition is vertical load. What is the case here? I have end here and I apply a force P. In this case, W is unknown and so is the slope, but the shear force is P and moment is 0. Moment at the end which I am applying external is 0. The fifth condition is moment. Suppose I am putting a moment of m here, then again W and slopes are unknown, but this is 0 and this is m. And then I can have another condition which is vertical load plus moment. So, I am applying a force P and I am applying a moment m, then again w and its slope are unknown, but these entities we know. Okay. In our case, so let us look at our case. We will consider that the beam is clamped at one end and it has some uniform distributed load, or it may or may not be uniform, but it is f of x. This is node 1, this is node 2, this is node 3, and I have a moment of m naught and I also have a force of f naught. So, for this situation, this case corresponds to that at x is equal to 0, right, w and w prime are 0, which means that u1 is 0 and u2 is equal to 0. What is u1 and u2? These are the degree of freedoms, right. And in the second case, so these are two boundary conditions, then that x is equal to L, Q5 is equal to P and Q6 is equal to minus M. Oh, it is actually F naught. So, these are the four conditions which I can put here. Here I can put minus m naught instead of q5, here I can put f naught, here I can put 0 and here I can put 0. And once I put that, then I have 6 equations and 6 unknowns, which are u3, u4, u5, u6 and q1 and q2. So, now I have 6 equations, 6 unknowns, I can solve and get all these values. Okay. There is another boundary condition which I did not talk about, and that is, suppose you have a spring at the end. Then what will be the condition at the boundary condition? So, in this case, are essential boundary conditions, and then we have natural boundary conditions, right. So, this is our shear force and this is our moment. So, W is known or unknown? W is unknown, right. We do not know what is the W. We do not know also the slope. We know that moment at the end is 0, there is no moment being prescribed, but there is also a shear force, and this shear force is equal to, if the deflection is like this is W, then the shear force will be trying to pull it. So, it will be equal to minus K times W. K is the stiffness of the spring and W is the deflection at this end. K times W, it opposes. Suppose deflection is W here, then this spring will try to pull it back, and that is why it is opposing the direction of WL. Okay. So, we can apply these boundary conditions in our original equation. So, that is what we will do. So, suppose my beam was clamped at this end, then what are the boundary conditions we will apply? U1 is equal to 0, U2 is equal to 0, and then Q5 equals minus K times U5, right, and Q6 equals 0. These are the 4 conditions. So, we go back and again put these modified boundary conditions. So, U1 we said is 0 because it is clamped end, u2 is 0 because it is clamped end, and moment was 0, and this we specify as minus k times u5. Okay. Now, when I solve this equation, I have to move this u5 to the left side. Okay. So, where does it go? Where does it go? First thing is that it will appear in the fifth equation. This is the fifth equation, right. So, when I bring this k in the fifth equation on this side, it will add up here. And once I have transferred it, then this side becomes 0. Does not mean that there is no shear force acting here, but it is that I have transferred that shear force here, and then later if we have to calculate shear force, I have to find q5 u5 multiplied by k, and that is my shear force. Okay. So, this is, so my stiffness matrix gets adjusted and this k appears here, and now I can solve for again u3, u4, u5, u6 and solve for it. Likewise, I can have another boundary condition, and it is that when it is bending, I have a torsional stiffness Kt. In this case, the moment in this, so this is a torsional spring. In this case again, W is unknown, W prime is unknown. Shear force, I am not putting explicitly any shear force, so that is 0, but moment is equal to what? Rotation, which is u6 times kt, and it opposes the rotation, so it is minus. So, suppose the torsional stiffness is kt, then this is there. Okay. So, then again if you want to implement this boundary condition, it will come in place of u6, and then you have to remove that kt and add it to k44 to solve for it. Okay. So, this is the way a lot of times we have springs also attached on beams. So, if there is a spring attached on a beam, then this is how you account for the stiffness of the spring. So, this completes our treatment for Euler-Bernoulli beams, and I hope you have understood what I wanted to explain. In the next week, we will have a small discussion on another category of beams known as Timoshenko beams, and then we will start discussing about eigenvalue and time dependent problems. So, thanks a lot and have a great weekend. Bye.